right, guys. So we are starting 3-5. I just had to show off my t-shirt because it's my rational function t-shirt. You shall not pass. Hopefully some of you get the reference. Go ahead and pull up your examples of graphs of rational functions sheet. You should have been able to print this off from the file folder for 3-5 in my math lab. Not my math lab, I'm sorry, in Blackboard. This is going to be a little awkward because I'm not used to doing these kinds of things without an audience. So, rational functions. We've just been studying polynomial functions, and if you'll remember, our polynomial functions are smooth continuous curves. Because they're continuous, that means that their domain is all real numbers. I can look at these pictures of functions on this page, and I can see immediately that the domain of these functions is not all real numbers. Just to give you an idea, the function are these curves here. Excuse me that my tracing skills are not great. This is the function, these two curves. And then for this one, here I've got these two curves where the function exists. They're smooth and they're curves, but they are not continuous. In fact, they are discontinuous for both of these. They're discontinuous for the x value 0. So my domain, instead of being all real numbers, is everything but 0. If I want to write that as an interval, I say from negative infinity to 0 or 0 to positive infinity where 0 is not included. A simpler way to write the domain is an interval notation where I say all values of x such that x is not equal to 0. So that's the domain of this function and a function number 2 as well. My domain is everything but 0. All values of x except 0. I'm going to go ahead and kind of divvy up my page so that I have space. I know where my space is for each of these 4 functions. Go ahead and look at functions 3 and 4 and see if you focus on the domain, if you can figure out what values you want to exclude from your domain. Notice that this one's kind of wonky, but my function, if I'm moving from negative infinity in a positive direction, my function gets closer and closer to this invisible line. And that invisible line is what we call a vertical asymptote. It's like a brick wall. It's like a brick wall. Vertical asymptotes are values that our function approaches and does not cross. We're going to have that in our notes section where you can write that down. So don't worry about it right now. Right now we're just looking at the functions to see what they look like and to see what we know about them before we even start talking about rational functions, because you know what these domains look like. My domain, I get closer and closer to that x value of 0, but I don't get there. So my domain for these first 3 functions include everything but 0. When I get to function number 4, I see that I have, instead of 2 pieces to my function, I have 3 pieces to my function. I have these 2 ends and I have the center piece with 2 vertical asymptotes. The vertical asymptotes, I've got one in a negative value and one at a positive value. We're going to identify those values that are being left out as positive and negative 1. Now I can get there by looking at my equation. Do you see the denominator on this function has x squared minus 1? That's difference of squares. Difference of squares factors out to give me conjugate pairs, x plus 1, x minus 1. And that's where we find our vertical asymptotes, the values that we need to exclude from our domain. So our domain for this function is everything except negative 1 and positive 1. All x values except negative 1 and positive 1. If I look at the graphs on the back, going ahead and thinking about domain, let's go ahead and divvy up our space. This function, it continues without ceasing. It's got this weird curve in the middle, but it doesn't leave anything out. So my domain here is all real numbers, negative infinity to positive infinity. That does not mean, however, that it's polynomial. If I look at my function my equation, I see that I have a variable in the denominator. That tells me that I have a rational function instead of a polynomial function. For number 6, I see that I've got this curve's interesting. It's got a hole, and then it goes off. I see I've got a vertical asymptote right there. I've got a horizontal asymptote here. I'm going to want to figure out what that value is and what the value of that hole is based on factoring this denominator. You know what, let's go ahead and do that. Let's look at factoring this entire function. Well, if I factor the numerator, there's my difference of squares again. So I've got x plus 1, x minus 1. If I factor the denominator, I can factor that quadratic. It's not difference of squares. My first terms are going to be x. The constant is positive, so that tells me that the sign in the factors, the binomial factors, is the same, and this middle term is positive, so that tells me they are both plus. 3 is prime, so my only factors of 3 are 3 and 1, so that's easy enough. When I look at my factors in the denominator, I see that I have one that matches a factor in the numerator, that x plus 1. So this function as written is not in lowest terms. I can factor that out, which means this value, if I set it equal to 0 to see what to exclude from my denominator, that value factors out when I put the function in lowest terms. If I set this equal to 0, I get x is equal to a negative 1. That negative 1 is the value for the hole in the function. This function, this factor, will not factor out. It stays. It gives me the location of my vertical asymptote. If I set that equal to 0, I get that x would be negative 3. Both of those values are excluded from our domain. So our domain includes all values of x except negative 1 and negative 3, because those are the values that show up in my denominator. Okay, let's look at this last function. It looks like a linear function, except it has a hole in the graph. So I need to figure out what the value is, what x value is excluded where the function jumps. And hopefully you've started to pick up that I find those values that are excluded from my domain by looking at the denominator. Well, if I take this denominator and I set it equal to 0, I get a negative 2. So my domain is going to include every x value except negative 2. Now my denominator doesn't factor, but my numerator does. Do you recognize that difference of squares again? Difference of squares factors out to give me conjugate pairs, x plus 2, x minus 2. That factor x plus 2 will factor out, it will cancel out and give me a 1, which is why it results in a hole rather than a vertical asymptote. Now, because you guys are not here to slow me down and talk with me, it is difficult for me to make sure that I'm answering all the questions you would have asked. So we're just going to do our best. We're not going to look at range right now. We're going to talk about symmetry, and then we're going to talk about those asymptotes, both vertical and horizontal asymptotes. Let's talk about symmetry first. When I talk about possible symmetry, remember we think about both what happens if I plug in a negative 1 for x and what the function looks like. I'm going to go ahead and make this bigger so we can zoom in on particular graphs. We think about what happens if I plug in a negative x and what my function looks like. Well, if I plug in negative x, I would have y equals a 1 over negative x, which is the opposite of a positive 1 over x. And when I look at the graph, I see I've got that twist in the middle. Remember that odd functions, the entire function value changes from positive to negative or from negative to positive. And my basic polynomial odd function is that cubed function where it's got the twist in the middle. Odd symmetry has that 1 up, 1 down, and it can be on either side, but an odd function that has odd symmetry about the origin is going to be 1 up, 1 down for the two sides of the function. This function is an odd function. It's symmetric about the origin. So I have origin symmetry. Over here, for function number 2, if I plug in a negative x, I would have y equals 1 over negative x squared, That's just 1 over x squared. Nothing changes. So when I think about symmetry for this function, I plugged in a negative x, nothing happened. I got out the original function value. That is what we call an even function, and it is y-axis symmetry. And you can see that when you look at the graph, because I could literally fold it on the y-axis, and those two sides are going to fold over and match. Those are the two types of symmetry we're interested in, odd symmetry and even symmetry. When I look at number 3, I can tell immediately it's not going to have y-axis symmetry. It's not going to be an even function, because if I folded it across and I mapped it over, this is going to veer off. It's not going to line up right here. So it is definitely not even. It could be odd. If I look at what's going on in those alternate quadrants, this veers off, that veers off. This approaches the y-axis, that approaches the y-axis. So let's do our symmetry test by plugging in a negative x anywhere I have an x. If I plug in a negative x, I have a negative x squared minus 1 over a negative x. Well, that numerator becomes x squared minus 1. It didn't change. The denominator is negative instead of positive. Now, when I write that negative in front of the x, because this is just a single term, I can leave that in my denominator, or I could pull that x out in front of my quotient bar, that fraction bar, and write it as a negative x squared minus 1 over x. That is an alternate way to write that function value. Whoops, that should have been circled in. Sorry, guys. There's my first plug. So from what I started with to what I ended up with, I have done the opposite. Instead of a positive value for this function, I have a negative value for this function. So this is an odd function with origin symmetry. Now let's look at function number 4 and apply our symmetry test. When we think about symmetry for this function, we think about plugging in a negative x. We've got y equals a negative x over negative x squared minus 1. Well, that denominator doesn't change again, the numerator does. So it is a negative x over x squared minus 1, which is the opposite of what I started with. So this is another example of an odd function with origin symmetry. And you can see that twist again in the middle, upper quadrant, lower quadrant. And then for my center section, I've got that cubed function twisting down. All right, let's look at symmetry for numbers 5, 6, and 7. Can you predict what's going to happen here when I check symmetry for number 5? If I plug in that negative x, my numerator is going to change, the denominator doesn't. Since the entire numerator changes sign, and I end up with negative x over x squared plus 1, that's like saying I have, say this was 3 over 5, positive 3 over 5. This would be negative 3 over 5. Well, a positive 3/5 and a negative 3/5 are opposite. So that is an odd function, and it has origin symmetry. Odd function, origin symmetry. This is helpful to us because graphing rational functions can be a lot of work. If I have something to narrow down what I'm looking for, I don't have to check as many points on my function, and I can save myself a lot of time. Okay, function number 6. My axes, my x and y axes are over here. So when I look at my function and how my function is shaped, that is not centered on the origin, because the origin is here. And it's certainly not centered around the y-axis. If I fold this function on the y-axis, the halves are not going to match up. So looking at the function as given, it's easy for me to know that I do not have predictable symmetry. If I need to do the work, though, if I'm going to check the symmetry before I graph to see if I can save myself some time on graphing, well, when I plug in a negative x in the numerator, nothing changes. When I plug in a negative x in the denominator, that first term isn't going to change, but that second term is. That second term changes sign. Since just a single term changes sign, but not the entire denominator, I do not have predictable symmetry. Not predictable symmetry. Again, looking at my function, I can tell, hopefully, that I don't have any predictable symmetry here. If I do the symmetry test, because I'm not starting with a graph, I'm just starting with a function. Again, when I plug in that negative x, my numerator stays the same. One term in my denominator changes. Just one term changes sign in my denominator. And if just one term in the numerator or denominator changes sign, then it is not predictable symmetry. Because that whole thing didn't change, just the single term changed. Okay, the other thing that is really important with rational functions are identifying where our asymptotes are. Now, like I said, I'm going to go through the guided notes in a minute, and we are going to get a definition written down of asymptotes. Asymptotes are values that the function approaches but never gets to. This vertical asymptote like we have here, that's like my brick wall, you shall not pass. Horizontal asymptotes aren't a brick wall. They're horizontal, it's not a wall at all. Mostly our horizontal asymptotes do not get crossed, but they can be crossed in the middle. If you look at example number 4, there's an example where I have this horizontal asymptote. The ends behave and notice that asymptote, but the middle section does not. The middle section crosses that horizontal asymptote. Now, that's what happens with horizontal asymptotes. They only apply to the ends. They do not always apply to the middle. So let's write down our equations of our vertical asymptotes. Asymptotes are lines. Vertical asymptote for this function is a vertical line where x is equal to 0. When I write the equation of an asymptote, it is always an equation. It is always an equation. So make sure that you write it as x equals, or if it's a horizontal asymptote, then it's going to be y equals. This function has a horizontal asymptote where y is 0. So that's the equation of that horizontal asymptote. Look at function number 2. I again have a vertical asymptote that happens where x equals 0 and a horizontal asymptote that happens where y equals 0. This is my vertical asymptote. This is my horizontal asymptote. Those asymptotes line up with the axes of my function, so the value is 0. This function's different. It has a vertical asymptote on the y-axis, so my vertical asymptote is x equals 0, but it doesn't have a horizontal asymptote. It has what we call a slant asymptote. Now we're going to talk about why that happens. You can have more than one vertical asymptote. You can have, for example, this function has 2 vertical asymptotes. You could have a function with 3 or more vertical asymptotes, but you are only going to have one horizontal or slant asymptote, only one, ever. Because that horizontal or slant asymptote tells you what happens at the ends of the function as x approaches positive and negative infinity. So you'll never have more than one. Now, okay, stepping aside, not this semester of college algebra, but functions exist where you can have different types of asymptotes that aren't lines. You could have cubic asymptotes. You could have parabolic asymptotes. We aren't doing those functions. We are sticking with linear asymptotes. The way you're going to know, and again, you're going to get this in your notes in a bit, but the way you know that you have a slant asymptote is that the degree of the numerator is 1 more than the degree of the denominator. My numerator is squared, my denominator is just x to the first. When I have that situation where the degree of the numerator is 1 more than the degree of the denominator, then I have a slant asymptote. And I find that slant asymptote by dividing, by treating this as a division problem. So to find the slant asymptote, I'm going to take that function as x squared minus 1 divided by x. So x squared minus 1, don't forget to put in your 0 placeholder, divided by x. What times x gives me x squared? Well, that's x. X times x is x squared, and then I subtract. When I subtract, that adds to 0, and I just bring down that -1. That -1 is my remainder. So I would come up here and say minus 1 over x. Now, remember that I said that our slant asymptotes and our horizontal asymptotes apply as x gets large, as x goes to positive and negative infinity. So think about as x gets large. If x approaches 1,000, that's 1/1,000. That's a teeny, 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 tiny space. If x goes to 1,000,000, that's 1/1,000,000. That's a teeny, teeny, tiny space. This remainder gives us the distance between that slant asymptote and the function. As I get further out, that function gets closer and closer and closer to that slant asymptote. It approaches it closer and closer and closer. It never gets there. When I list the equations for me to be able to graph the slant asymptote, I don't worry about that remainder. I just drop it off because that's that little bitty space that's always getting smaller. All I worry about is that quotient without the remainder. So my slant asymptote equation is y equals x. Graph number 4 goes back to our nice simple horizontal and vertical asymptotes. I have 2 vertical asymptotes. If I look at my denominator, I see the values I excluded from my domain are positive and -1. Neither one of those factors out my functions in lowest terms. So those both give me equations for vertical asymptotes. So my 2 vertical asymptotes are at x equals 1 and x equals -1. I have a horizontal asymptote that falls on the x-axis. So its equation is y equals 0. All right, moving to number 5. Look at your graph. You don't have a vertical asymptote. My domain is all real numbers. I didn't kick anything out of my domain. My domain is all real numbers, so there's no vertical asymptote. I do have a horizontal asymptote. It gets crossed in the middle, but I have a value that my graph gets closer and closer and closer to and never quite gets there. I have a horizontal asymptote at y equals 0. Y equals 0 is the equation of my x-axis. For number 6, I have both a horizontal and a vertical asymptote. Well, my vertical asymptote is at -3. That's that value I kicked out of the domain that remains when my function's in lowest terms. And I have a hole in the graph at x equals -1. Because that value is not going to stay. If I put my function in lowest terms, that will cancel out. So I have a hole at x equals -1. I have a vertical asymptote whose equation is x equals -3. And then if I look at this horizontal asymptote, I see that it is raised above the x-axis. Now, in our notes, we're going to discover that when we have a horizontal asymptote that is not on the x-axis, that occurs because the degree of my numerator is the same as the degree of the denominator. These are both squared. The degree of the numerator is 2, the degree of the denominator is 2. When that happens, I look at the ratio of the leading coefficients. I don't have any coefficients written there. If there's not a coefficient written, we understand it to be 1. So that equation is y equals 1. All right, number 7. Do not have a vertical asymptote, because if I look at my function, it's not in lowest terms, that's going to divide out. That value that gets kicked out of my domain, x equals -2, that's a hole in my graph right there. Where x is -2, the function does not exist. Do I have a horizontal asymptote? I do not. Do I have a slant asymptote? I do not. If I look at my function in lowest terms, that cancels out and it just becomes x equals 2, which is why this function looks like a line with a hole in it. Okay, now, ideally we would have been talking about this in class while we went through it. That couldn't happen this semester for this class. So I'm going to encourage you to remember that this video exists and to come back to it after we have gone through the notes section.